Okay, so today we're going to be talking about the thermodynamics of heat pumps. So give it a thought. How do we get that heat from the cold outside ground? And look at the answer here that I have on the screen. And just remember from last week that heat is present. So anybody who tells you you can't get heat from the cold, right? You can't get heat from a cold environment. Yes, absolutely you can, because heat is present in all substances down to negative 273 degrees Celsius. So air at 0 degrees Fahrenheit has more heat in it than air at negative 20 degrees Fahrenheit and less heat than air at 40 degrees Fahrenheit. However, there is still heat in it. Okay, so a heat pump, and I know I say this a lot, a heat pump basically moves air in the opposite direction, right? So it's going into a cold environment to get heat, to deliver that heat to a warmer environment, which is kind of neat. Okay, and how do we do that? We do that, and a heat pump transfers both ways. So a heat pump actually cools and it heats. So that's pretty cool. So it is a total, and it's called an electric system. And the reason why it's an electric system is because what you're paying for to do this is the compressor. All right, so it's going to move that refrigerant in order to heat and cool. So in heating mode, it moves the heat from outside to inside. In cooling mode, it moves it from inside to outside. All right, so why do we say heat? Heat has a level or intensity, and it has an amount of energy in joules or BTUs. Joules or kilojoules and BTUs. And then pump just means it makes something move in the direction it wouldn't ordinarily go. So I'd like you to think about the fact that it's moving in a direction opposite to how thermodynamics would normally make things move. So let's take a moment to remember how our heat pump gets put together. So you could do this in group work, but I'm feeling like everybody's kind of not awake until 10 o'clock. So I'm just going to do this for you, and then we're going to go on our break. Well, I'm going to do it with you. So if you remember that your heat pump, because a heat pump is a refrigeration cycle, right? Remember, a heat pump has 4 elements. So I'm going to make this slightly interactive just to keep you awake, but I'm not going to make you do it yourselves. Slightly interactive means I'm not going to write anything until you put it in chat window. So you tell me, what do I need to include? A compressor. All right, let's start with a compressor. We usually stylize a compressor to look like this. And we're going to have an evaporator. So if this is my compressor, well, my evaporator can be on any side, right? I have a compressor, evaporator, condenser, and expansion valve. Well, you pretty much got all of it there. All right, everybody's waking up. This is good. So I'm going to put, is this a evaporator or a condenser? You don't know because you don't know which mode this is in, right? So I'd have to tell you which mode it's in. All right, here we go. And then you said there's an expansion valve in there as well. Expansion valve, you don't know if it needs to expand this way or if it needs to expand this way, because again, this works in a couple of different directions. So I'm going to call this, I'm going to give this some context, and I'm going to say that this is indoors and this is outside. And unfortunately, this is an air-based exchange. And what I'm trying to help work on is this being a water-based exchange, but right now, all you can really buy is an air-based exchange. I'm going to put in brackets, water-based, a little bit available now, but it is better. It is rare right now. And I hope that I teach this in 5 years from now. And I hope we say it's water-based exchange on this side because it's better, right? Water-based on this side, very difficult unless you have the land for it and you get to do geothermal. So air-based exchange is fine. It's fine for where we are right now. I'm just going to say what we want to heat this. Okay. So, outside it's cold and indoors it's warm. It's warm, but we want to heat it. So I'm going to say we're in heating mode. So if we're in heating mode, this is the direction that we're going to be moving. So then what is over here on the indoor coil? And just call this the indoor coil. You tell me what it is. Is it a condenser or an evaporator? Look into the chat window. Look into the chat window. You should be able to quickly say whether that is a condenser or an evaporator. Yes, that's a condenser. That's a condenser because it's a condenser in heating mode. That's your evaporator in cooling mode. If I want to cool, then I want to take energy out of this, right? If I want to cool, then I want to like I would have a liquid and it would be turning into gas and I would be stealing the energy from the room if I want to cool. But this is in heating mode. So I want to condense that fluid. It's easier to think about the evaporator. The way you can think about this evaporator is needs to steal energy to evaporate. So excuse my kind of, slang words there. It needs to steal energy to evaporate. This is a condenser, gives out its energy, right? It loses that high temperature and it's losing that heat energy and it's actually going to start condensing. Whereas on this side, in order to evaporate, it needs to steal a lot of energy. So it needs to get hotter. In order for it to evaporate. So let's talk about temperature. And what we're going to do today is we're going to actually make some diagrams. Okay, so we're doing what's called a PV curve. We're going to do PV curves today. And it's something that you haven't learned about heat pumps yet. You have learned this thermodynamic cycle a couple of times though, but we just need to remember it so that we can do our PV curves. So in order to do our PV curves, I want to talk about the pressure and the temperature at each of these corners, and then we'll go on our break. So I'm going to have you do it. Okay, the slight interaction, we're going to ease you into some interaction so it's not so boring here. I'm going to have you do it. So I'm going to have you choose a place to look at first. You can choose this corner or this corner, this corner, or this corner. So tell me about the temperature at one of these corners. Where is it the hottest? Yeah, very, very, very hot here. It's the hottest, right? So it is the hottest. Oh, you're actually writing it on the screen. That's great. Very, very hot. Okay, why is it so hot there? And that's right. It's very, very hot. Why is it so hot?
It's very hot there because it just came from the compressor.
Why did we put it through a compressor?
We wanted to make it as hot as possible before it goes through the indoor air exchanger.
Yeah, because the ambient air here is pretty warm, so it better be hotter than ambient air, right? So it's a very, very hottest there. What about pressure? And you can put the answers in the chat window or annotate on the screen. Actually, why don't you all annotate on the screen and get all 4 corners done at once? Everybody, annotate on the screen. Jack, I can't read your annotation. What's this saying? Is this saying really high pressure? Yes. Okay, high pressure. I'm going to rewrite that for no reason. No reason at all. Here we go. I'm going to rewrite that. So that's going to be the highest pressure, right? Highest pressure. Because it just came out of a compressor, and the compressor's job is to make really high pressure, right? Everybody try some different corners. Try to race me, okay? Race me. So I would say that we're about to go into, oh, there, somebody did this. This is great. It's going to be very cold here, and it's going to be low pressure because it just got expanded. So lowest pressure. It just went through the expansion valve, which now looks like this, right? So it expanded. That means that pressure decreased, right? And it got coldest, right? T coldest. Why did we have to expand it to make it so cold? Because outside it's pretty cold and I still need to grab some heat from outside, right? So this is my cold ambient air. And this is what everybody's arguing with me about, is saying, but it's cold outside. Cold ambient. So what do? You just make it colder, then cold. You make it colder, then cold. Sure, it's cold in Canada. Yes, make it colder, then cold. Use a refrigerant that you can expand. You can make even colder. What's going to happen if you make it colder? It's going to absorb Q, right? Maybe that was like a little too thick. And then if this was really, really hot, it's going to lose its energy, its Q, right? Okay, so you're not doing very well at the other corner, so you're going to race me. What's going on here is, so it's still pretty low pressure, right? It's still low pressure here. It's a little bit higher temperature. T high. So it absorbed this this energy. It got pretty high, but not as high as it'll go higher through the compressor. I'm winning the race so far. What is the pressure here?
That would still be the low pressure, right?
Exactly. And why is that? Why is the pressure still the same low pressure? Oh, Jack's beating me.
I think this is basically just one tube, right? Like there's nothing
exactly
in between, so the pressure is going to be the same everywhere.
Yes, you were listening to me last year, right? You were listening in HVAC class last semester. This is just a tube. There's no compression, there's no expansion, so it's just that same low pressure. All right, and Jack's got it over here. This is temperature, warm. It used to be very hot, but look at it, gave away all of that Q in red. And then, but as Adam said, this is just a tube. There's nothing compressing, there's nothing expanding, so it's still high pressure. All right, so we've done a good job of messing up another thermodynamic picture. So thanks for participating in that. Any questions on this?
Yeah,
because
Karen, I have one question. So
yes,
we know that there's a valve that reverses the direction of the coolant or whatever,
yes.
but a compressor will only still have one inlet and one outlet, right? Like you can't reverse the direction through the compressor. So there must be a valve that like allows that change to happen too, right? Or am I wrong?
Um,
Can you have
well,
like bi-directional compressors? Does that exist?
no, it's switching, it's still going into the compressor the same way and it's switching it on the loop. So it like on the actual loop that's going to go into the compressor. I'll show you in 1 second. So let me just stop your annotating here or erase your annotating, but thank you for participating. Here we go. So now I can scroll. So here's what it actually looks like. So the valve that you're talking about is right here. So when you switch that valve, it's just switching the pipes.
Right.
So
Yeah, I see that. I see
see
that.
that?
Yeah.
So you're still going to be coming out of the compressor and into the compressor the same way, but it's going to be switching. It's switching up here, switching there and there.
Yeah, okay. Yeah, I kind of figured it would be something like that. I just thought I'd ask about it.
Yeah. So let's take a moment actually to think about this before we go on our break. Okay, so this one is actually this one's actually going into water, right? This one is this is a geothermal heat pump because this says it's a water supply and a water coil. So this is geothermal. So this is water-based outside. And we say geothermal for obviously geo means earth, but it could also be, a pond loop or something. We still call that a geothermal, but it's a water-based exchange. All right, we've got our expansion valve, our compressor with that reversing valve, and then here it's just going through your evaporator or condenser, depending on which way it's going. And then this example is just a typical forced air furnace. So what they'll try to do in a giant house like these, like the ones that I showed earlier, is that they will try to go air based over here. One of the things that they'll try to do is go air based over here, which isn't going to bring as much thermal energy in, and they'll try to connect it to the same furnace used to be natural gas. So as we're in this progression to heat pumps, some silly things like that are going to happen. And this is happening, right? So they put this air exchange outside and they connect it to a furnace that, this is connected to all of your ductwork and, the vents in the floor and return and everything. And there's just simply not going to be enough heat in that air in order to do this air-based forced air furnace, air-based exchange. Because you have losses out here where you're getting the heat, and then you have losses here in this air-based exchange. Much, much better to go geothermal on this side, but it's impractical in most cases. You're going to have to start making up for it here. And in new construction, this is going to have to start going water-based.
But right now with like retrofits, if you were to get a heat pump right now, this is what they would do, right? With just put it into your sort of previous natural
Yeah,
gas furnace.
exactly. That's what they're doing, is putting it through this original ductwork. So, but then they tend to be undersized on this side. So what they're doing then to deal with the undersized is that they put in this air based on this side. And then you say, oh, it's undersized here because everyone's living in these mansions, right? And then you're not getting enough heat through your ducts that are, there's a lot of heat loss in ducts too, right? As you can probably imagine, knowing something about fluids and thermodynamics, there's a lot of heat loss in air-based ductwork as well. So then what they're doing is they're supplementing. So here's your giant home. Here's your giant home. You already have the ductwork coming through with that furnace. Now you're going to, in the living room, you're going to put a little split system with that little, condenser unit inside. It's a little split system, just like you did. You know what I mean by the split systems in the HVAC lab, right? On the little rolled out cart? Yes, no?
Yeah, and then they usually hang sort of near the top of your wall in your living room,
Yes,
sort of thing.
exactly. So you're going to supplement all these rooms. Master bedroom is really big in these houses. I'm not insulting anybody who lives in in a big house like that, but they are definitely grand. So there you go in that room, and then maybe you need like to supplement in this big like 2-story windowed hallway or whatever, right? So this system is too small just because of those losses. It is electric, yes, because you're paying for this compressor. That's it. You're electric. You've eliminated fossil fuel. That's great, but it's too small for a lot of these systems. So you're going to supplement with this split ductless. These are called split ductless. Okay. As opposed to in new construction, if you could make this water-based, then this could be in a radiant hot water floor. And this could be doing its heat exchange inside a boiler. And it will be a water exchange inside a boiler. And then you could dissipate it across a radiant heated floor, or you could dissipate it to radiators, right? Here, I'm golden old-fashioned 1940s radiator on your wall. And then this water-based system would have enough energy to transfer. So hopefully that's where we're going. Exciting. And I pulled a presentation. I've actually, at this point, I'm working with somebody who is trying to push this through Natural Resources Canada. It's somebody who owns a company that does this. And I have a presentation that he gives often. So I'm going to bring that presentation into our lecture today. Okay, so at this point, let's take a 10-minute break. I will see you at 10:15. I'll put that here, 10:15 back. Okay, thanks so much for coming early. I will see you at 10:15. Pump. Still doing our heat pump thermodynamics. So hopefully you've taken a break here and gotten what you need to be nice and refreshed for basically our 10 o'clock class now. Okay, so let's talk about the thermodynamics of this. This picture is just the same thing, and it has changed modes, so it really shows how that that compressor is still going the same direction, right? This is still going in, and this is still going out, and it's this is cooling mode, and this is heating mode. Okay, so let's work out PV curves. So it's common to draw the relationship between pressure and volume on a PV curve. And this is what helps us understand the thermodynamics and the eventually efficiency of the heat pumps. So I'm just going to quickly draw our thermodynamic cycle here again. I won't take up too much of your time to do that. I'm going to put the compressor at the top and the expansion valve at the bottom, just like you had it. And we're going to put it in heating mode. With the indoors here, all right? Just like we had before. So if I take this diagram then, and I divide it into some quadrants, then we can talk about what's going on with pressure and volume across each quadrant. So I'm going to number these quadrants. I'm going to number them 1, 2, 3, and 4. And I'm going to be doing we are going to develop the pH curves across across the device at 1, 2, 3, and 4, not at the corners that we were talking about before. So if we're going to do PV curves, PVs are it's the relationship between pressure and volume. So we're going to do that at 1, we're going to do it at 2, we're going to do it at 3, and we're going to do it at 4. All right. And how this is going to relate to your final exam. Would you like to know how this relates to your final exam? On your final exam, I'm going to ask you, what can we change about this pressure volume relationship to make a more efficient compressor? Or if I give you 2 of these diagrams, can you describe which one gives more heat to the room, or which one is has a larger compressor, smaller compressor? Okay, so that's how this is going to relate to your final exam, and I'll mention that a few times. So we're going to look at the relationship between pressure and volume at all of the different parts across these devices. So device 1 is our compressor. Device 1 is a compressor. What happens across the compressor? The volume is increased, right? So across that compressor, I have a situation where I'm getting high pressure here. And just stop me if you have any questions. Or just yell if you have any answers to some of my questions that might be rhetorical, or I'm welcoming an answer to them at any time. So here across that compressor, I have high pressure on one side and low pressure on the other side. But as Adam was mentioning, there is no more change to the volume here. So there's not a compressor, there's not an expansion valve, there's nothing else that changes the volume. Therefore, we can say that this entire line is a high pressure and low pressure line, right? This entire line is a high pressure and low pressure line. So across that compressor, what it's called is called an adiabatic process. An adiabatic process, anybody know what that means? It means no something is exchanged. With the surroundings. No what? And this is not on the exam, okay? I'm not going to ask you what adiabatic means on your exam. I'm going to ask you to apply this.
I'm assuming it's heat.
Yeah, exactly. So thank you so much. No heat is exchanged with the surroundings across the compressor, okay? Because we don't want it to. I mean, some heat does get exchanged, but we don't want it to. So let's say that let's say this one here is a compressor. And if we're going to look at the pressure, then the pressure definitely is going to go from a low pressure to a high pressure, right? But the volume has also changed. What has happened to the volume? So I must have to go from low pressure to high pressure. I must go in between these two lines. But what has happened to volume? This is high volume. This is low volume. Do I go from high to low or low to high?
You go to from high to low if you're increasing the pressure, right?
Yeah, you're decreasing that volume. That's how you increase the pressure. So you used to have a pretty high pressure going into one, and then you have a lower pressure going out. So you used to have higher volume going in, and you have a lower volume going out. So what we have here then is we used to have high volume, low pressure, and what you ended up with is here, and it is low pressure, low volume, high pressure. And in between, there's sort of a curve that I can't describe mathematically, but there is a mathematical description for this curve that could be determined experimentally. What I'm saying it doesn't go straight. So we can now call this T1, P1, V1. Temperature, pressure, volume at point 1. This is temperature, pressure, and volume at point 2, which is higher. Okay, good. So now I'm going to ask you to fill in this one, and this one. I'm going to put you in groups, and I'm going to give you only 10 minutes to do that. And then you're going to come back and you're going to try to scratch them on the screen. In groups, 10 minutes to do that. Wakey, wakey, everybody's awake. So in groups, 10 minutes to fill in the last 3. If you don't have them, take a picture, take a screen capture of this right now and try to draw on them, okay? So everyone's like, I thought she was going to be telling me all this. I will also tell you all this, but see if you can come up with it in 10 minutes. Let's see. I'm going to make, I don't want too many people in each room. I'm gonna make 5 rooms. All right, in your room, come up with the answer to this. I'm going to randomly ask somebody to present it when they come back. And this is how we get real work done. Here you go. Opening the rooms. Have fun. Zoom recording. All right, I kind of cheated a little bit. So I said that there's high pressure once you compress and it stays high pressure. And I lied. And then I said once you increase that pressure again through an expansion valve, then it remains low pressure. And again, I am full of lies. What actually happens is it stays high pressure. Yes, it stays high pressure. However, you're losing that heat energy. Q is leaving. So some of those molecules are shrinking. So this is actually a little bit less. It's a little bit less pressure because there's the same volume, but a little bit, there's more room for that substance to fit because some of those gas molecules turned into liquid over this is the condenser. And this is the evaporator. So again, I'm full of lies here too, because actually, as you go through the evaporator, you have liquid turning to gas. Gas takes up more space than liquid, and you haven't given it any more space. So a bit of pressure change. Okay, so I hope that me messing that up and lying about it will stick in your head so that when you're on the final exam, you really remember that because you were told one thing and then another. Okay, so here we go. Let's, with that in mind, say what happens over this condenser. So again, on this side, they're still going to stay pretty high pressure. So here was my high pressure line, and it started at as we went into this, we have to be at that same point. So the screen share that you gave kind of had it in the middle here, and then you said straight down. So you're right, but let's actually observe the fact that we are actually at T2, P2, V2 here as it goes in, right? Give or take a tiny bit of pressure that might have changed there and a tiny bit of temperature that might have changed. But in general, going into that condenser, and let's say number 2 is here right before you go into the condenser, then you can say I'm at this point, right? And then I'm going to hold volume constant. So as you said, it has to stay in the same vertical, and because it's a constant volume, but the pressure is going to relieve just a little bit because some of those gas molecules are going away. So right here, I would say that this is the temperature, pressure, and volume of 0.3. 0.3 is going into that expansion valve. So if I said, okay, I in general have some low volume and high volume sides, and I in general have some high pressure sides, and I have some low pressure sides, then, well, I should put those on the diagram here as well, is that basically I need another line. I'm going to need to really mess up this diagram. I'm going to go here, and I'm going to say that this up here tends to be gas. Well, we hope, because we don't like putting liquids through a compressor. Down here, it tends to be liquid. Okay. So where am I right now? I'm right here going into the expansion valve. So I start my expansion valve at here. T3, P3, V3, right? And then I'm going to end it. I'm going to expand the volume. So I must be going this way to this high volume line. And then what's going to happen to pressure? That's going to dramatically decrease the pressure, right? So I must be on this pressure line. So if I take this arrow, connect it to this arrow, then I'm down here, which is exactly what was presented. So that's where we get to TPV4, which is going to go across the evaporator. And it's a similar type of curve that went across the compressor. So now we're going to look at the evaporator, and we're going to want a constant volume. What kind of volume? Is it going to be low volume? Is it going to be high volume? Well, we just expanded, so we should be on the high volume line. So we started at this high volume line at TPV4. And it's going to pressurize a little bit because of those molecules turning into gas, and TPV5. 5? No, 1. We should be getting back to TPV1. Oops. 1 TPV1 should be here going into the compressor. Any questions about that? Point 1, 2, 3, 4 going across compressor, condenser, expansion valve, and evaporator. Pressure volume. You've done in your other class, you did pH curves. You did pressure times enthalpy curves. And if you remember, that's when you had this diagram. I think, Jack, what you showed or I don't know if it was Jack or John, but what you showed looked more like a pH curve with some losses, which is what you did last semester. But it did say V at the bottom here. So it didn't make too much sense to me. So I would be careful about that curve. And maybe you did get it from a heat pump, and maybe it's saying something else, but I'd be a bit careful of it. And I just want to kind of skew you in this direction because I specifically want to, quite honestly, ask you about something on the final exam. Let's do a little summary of what we saw over here then. So what we saw, first we went over the compressor. That was an adiabatic process. Step 2 was across the condenser. And it loses heat. don't forget, that's the point of either losing heat or gaining heat. Therefore, loses a bit of pressure because of the molecules, and then volume remains constant. Just in case you have to describe this with words on the final exam, I'm putting some words here to help you describe these charts. And then 3 is across the expansion valve. Across the expansion valve is, again, it's an adiabatic process. The gas decompresses. Therefore, it expands. Right? The expansion is the gas no longer compressed. And as it decompresses, the temperature drops really low. Has anybody played with like something, a situation where you expand a gas very quickly and the temperature drops? Has anybody done any work where that has happened?
I just know if you go camping and you're using those like little green propane canisters, they get frozen on the outside, right?
Yeah, exactly. So whenever you're disconnecting your propane tank, and yeah, the little green ones, that's a little bit better, right? Because there's not, because they're small, but that'll happen with with a big propane tank too. When you undo it and that propane comes out so fast that you've expanded it to the point that you have reduced its temperature, and it'll all cake up on there. And so this actually happens on a heat pump as well. So the outside of a heat pump, and a heat pump is, that a heat pump is just an air conditioner too, right? Like, does everybody know that all the condos around here that have that little unit outside, the AC unit, this AC unit that looks like this, it's sitting on every one of those stacked townhouse condos that are so awesome and chic. So you have this little heat pump system, and then it has some lines going into all the condos here in Kitchener, Cambridge, etc. This has an indoor coil as well, and this is just the outside coil, and they call this AC, but this is just a split heat pump that works in one direction, because those condos actually are also burning natural gas in either a radiant heated floor or a forced air system for every single unit. But these AC systems, these are just split heat pumps. And they're just running this thermodynamic cycle, but they only run it one way. So do you know what I mean by these little units? Like an AC system used to be like a window shaker that you put in your window. But these little systems are basically heat pumps. So what happens with these systems is they actually, when run as a heat pump, they're actually going to get frozen on the outside. So their coils are actually going to get frozen, and they actually need a defrost mode. And their efficiency is going to really drop when they frost up, and to deal with the frosting up, they just basically turn off for a certain amount of time and wait for defrost to happen. Okay, so expansion valve, where was I? Okay, 4, what is 4? This is an evaporator. So again, to give you some words to help describe this system, it gains heat, receives heat, heat is transferred to it, okay, gains heat to increase temperature and pressure a bit. All right. So those are some words just to describe what we've done so far. So let's do the summary of this system. So this is what's going to be really important. And I'll just tell you one of your final exam questions right now. I'll say how to make more efficient. Less efficient. What if, so I'm going to ask you, what if you buy a worse compressor? Redraw this curve. What if the energy can't be transferred from the inside to the outside? What happens when the ambient air temperature outside is really, really hot and you're in cooling mode? What changes on this curve? What happens inside if you could transfer this heat to water versus to air? What would work better? And if it works better, what would the curve then look like? Okay. What would new curve look like if ... various scenarios? Okay, this will be an online exam. You will also have a Dropbox to put a sketch. So on your Econs Toga question, let's say you got a question of saying, instead of this, like this is a PV diagram for an air-to-air heat pump, what would a PV diagram for an air-to-water heat pump look like? In heating mode. Well, then what would happen? The energy transferred into the room, there would be more energy transferred into the room, wouldn't there? So there would be more work done by the system, less work on the system. So the cost would be less and the energy would be more. Know where I'm going with that? So different scenarios. If you were eager for more group work, I could put you in group work and you could come up with a lot of scenarios and then try to answer them yourself. Or you could even make a game of this, of asking people different scenarios and answering them, kind of a practice for the final exam kind of game. But I'm not so sure how eager you are to do more group work. And I already have another group work activity for you today. So let's take a look at sort of the normal case, sort of an ideal. We're going to do air to air reversible heat pump in heating mode. Okay, that's what we're going to do here. And you're going to be able to come up with different scenarios. So we had a high pressure line and a low pressure line, and we have a high volume and a low volume line. And I'm just going to transcribe onto here those points that we made together. And what we had at the top and the bottom most points were 0.2 and 0.4. So if I look at them here, oops, this is when whiteboards are a little bit easier. So I wouldn't do something like that. I would just, walk over. Uh-oh. I've overwhelmed the computer. We have to pause for a moment for it to come back to life. So you see that now my grid is offset from my points here. All right, it's back to life. Let's move this back. All right. I'm not going to scroll. You look at your notes. But 0.2 and 0.4 were the ones that you had just gone into what had you just gone into? You had just gone into the condenser and you had just come out of an expansion valve into the evaporator. So you just came out of a condenser at the top there and you said, all right, well, pressure doesn't change, but it changes a little bit. Pressure doesn't change, but it changes. And there we go. Pressure changed a little bit because you gave a little bit of relief to that pressure there. And just having trouble drawing. You gave a little bit of relief to that pressure, and then that's going to be, that's right here through your condenser. That's T3. And here across your evaporator, you across your evaporator, you gained a little bit of pressure because it got energy from outside. Those molecules got a little bit bigger and here gave energy to inside because this is in heating mode. It's a heat pump in heating mode. And then in between there, you had your compression and you had your expansion. Can you hear snoring in the background? My black lab, he snores. And it sounds like an old man. All right, so this is the energy that is transferred into the room is right here. And then this is the energy that got transferred from outside. So what did we actually do this for? We went outside, we got some energy, right? And then we transferred it. So this is what we did it for, right? It's in heating mode. We actually did it just for this. This whole thing is for this. This is the purpose. This is the purpose of the entire system is this side. It's right there. It's transferring that energy into the room. And then why aren't you correcting me? Big problem here on the screen. What's the big problem?
You reverse the expansion and the compression.
Yeah, exactly. No, I was about to threaten a free exit ticket for correcting me.
Oh,
Compression.
Answered too soon, Adam.
yeah, I know. I'll just, okay. Yeah, it's too soon, sorry.
It's okay, Adam, you can have a free exit ticket. You seem to be right on the ball, knowing what's going on today. Maybe I'll give out more free exit tickets. That's what keeps people engaged. All right, so that's the energy transferred into the room. But what we need to look at is what is the work out of the system? What is the work into the system? And then we're going to talk about the net work that we actually got done. All right. So what is the work that we put into the system that we paid for? What did we pay for? Now I'm going to write down names for free exit tickets. What did we pay for? The area under the curve. We're going to do the area under the curve is work. Area, which we could prove, under curve equals work. So where's the part that we paid for? What is the work that we paid for if we were
the
to
electricity?
Sorry?
The electricity that we put into the heat pump.
Yep. Where does it go into the heat pump?
We pay for the compression, right?
We pay for the compression. Sorry, I have to start my video, even though it's just my roof, because I can't see who's talking unless my video's on. I'm not sure if that's normal. Wait a second. Now it's not. Oh, is it because I'm screen sharing? Who was just talking? Was that John?
That was Jack.
That was Jack? All right, good, Jack. So yes, you're paying for the compressor. You're paying for that system. So the area under this whole compression curve is the work that goes into the system. Okay, this area under this whole curve is the work into the system. The area, so then you transfer some energy inside, you got some energy from outside, and the work that left the system, so you paid for this work energy into the system, the work that got out of the system is the area under, anybody have a guess?
Under the expansion curve?
Yes, it's under the expansion curve. So this is the work out of this system. So green, work out of system. The system did work on its surroundings here. So the work into the system that you paid for, work out of system. This is happy face, right? This is the work we wanted. So what is the difference there? Is it good or bad or ugly, or what is it? What's the difference here? Any thoughts?
That heat pump's pretty efficient
Yeah, and how do you know it's pretty efficient?
because the work out and work in are fairly similar.
Right, exactly. So this is basically the difference between the two. So you could say that this is the net work. This is the net work into the system. This is what you sort of, excuse me for being so casual in explaining this, but this is like your extra money, right? It's like you paid for this to happen, so you're happy to pay for this, but you actually paid this whole amount. So the extra amount that you paid for is this. So it's kind of like your losses, right? You got a little bit less than you paid for. So that's the net work into the system. So it's the net, I should just say it's the net cost. The net cost, because a lot of that cost went to your gains, but this is your net cost. Okay. All right. Now, I'm going to put you in a room, and you don't have to present to other people, but I'm going to give you an exam question. Okay. So I'm going to put you in your room, and I'm going to give you an exam question, and your exam question is going to be, I'm going to give you all the exam questions at once. So I'll put them in the chat window so you can copy and paste them. So everybody take some time right now to take a screen capture of this picture, and I'll put your exam question, like literally, this is your exam question, okay? And you're going to try to answer it together, because some people are good at this and some people might not know what's going on. So let's get everybody up to speed so that everybody gets to study less. So here we go. Exam question. Redraw the curve, or I'm just going to say, like on the exam, I'm going to say redraw the curve and explain it. But right now I'm going to say, think about how the curves would change if the compressor compressor and expansion valve. And the evaporator and the condenser were like one at a time. What if the compressor were more efficient? What if now the compressor is the same? What if the evaporator is less efficient? What, because you haven't like cleaned out the grate and it's full of leaves? What, now put that back the same. What if the condenser is like full of gunk in your house and you decided to store all of your extra suitcases you don't use anymore because of COVID, are all shoved up against it, so it can't do any airflow? How does that affect the curve, right? I would never ask you to change the efficiency of more than one component at a time, because then a lot would be going on. So your exam question is, think about how the curves are going to change if the evaporator or the expansion valve or the condenser, all four units were higher or lower efficiency. I want you to go into your rooms and I want you to run through some scenarios as if you're on the final exam. On the final exam, you'd have to redraw it and explain what has happened. Okay, so in your rooms for 10 minutes doing that, please.